Hey everybody, welcome back. This is the last installment of your practice final exam for your statistics class. This will be problems 35 through 44, and let's go ahead and jump into it. So once again, I'm assuming that you have either a digital copy of this or a paper copy of this that you can download from Canvas at any time, the practice final exam for stats. Number 35. They give us this, and all they want in this case is the critical value z used for a null hypothesis. They give us that alpha is 0.09, and all they tell us is that it's a right-tailed test. And as always, I like drawing a picture. And they specifically say the critical z value, so I don't have to guess whether they meant t or not. These are z's. And it's a right-tailed test. So this here, this area, 0.09. And when we use this here, we have to use inverse norm, but if you recall, inverse norm only knows area to the left. So I'm going to do my 1 minus 0.09. So the critical value in this case, and there's only one because it's a right-tailed test, 1.3408. Do they say where to round it off? They do not. So there's our critical value. This is the critical value. All right, we're moving on. Number 36. So they want to find the p-value on this one. They tell us that alpha is 0.05. And they want us to come to a conclusion, so that's fine. So our null hypothesis in this case is our proportion is equal to 0.221. Our alternative hypothesis, they tell us, is the proportion is not equal to 0.221. And they tell us that the test statistic is z equals 2.21. Let's go ahead and set up our critical region. And this is a proportion, so we're using, excuse me, z, pardon me. And because it's not equal to, it's a two-tail, so my alpha gets split up in half. So I'm going to find my critical values. So I'm going to do inverse norm. I'm going to do this one first, 0.025. And we get negative 1.96. And this will be a positive, but I'll show you how we get that as well. We do our 1 minus 0.025. And you can see it's positive 1.96. In this case, we have two critical values. All right, now we already have the test statistic. And 2.21 is way over here. And we are definitely in the critical region here. Now we could find the p-value, which is what they want us to do. Now we have to be careful with this. If I find the area from here off to infinity, that's only half the p-value. I'm going to have to double that because it's two-tailed. So I do. So this is going to be half the p-value. And I'm going to do, norm CDF in this case. Here's the 2.21. The upper is just some big number. And this is only half my p-value. Oop, I'm missing the 0 in there. So to find the p-value, I'm literally going to double this times 2. And that's one of the answers that they're looking for. But right away, I can see that is definitely less than our alpha, which is 0.05. So what conclusion can we come to? We're going to reject the null hypothesis. And that's all that they wanted for that one. So we have some full hypothesis testing here in just a second. Number 37, next page. And I don't like that I just have a little bit of room there. I'm going to go ahead and flip my page. .37. And I'm going to notice before I start even reading the problem that I have a bunch of raw data. And you may need to pause the video, but I have already put the data into column 1. And we're going to do a full-on testing with this one. So a simple random sample of 15-year-old boys from one city is obtained, and their weights in pounds are listed below. Use let me write this down, alpha 0.01 significance level to test the claim that the sample weights come from a population with a mean equal to 150 pounds. Now I'm going to change that, and a mean not equal to is what I'm going to call that, so that the claim is on the alternative hypothesis. So my statement's going to look a little different than the answer key. Conclusion will be the same. And we have all of this going on. Now they make a big deal and say that the population standard deviation is known to be 16.4. Excuse me. So let's draw this up. This is going to be two-tail. And so that's half of our alpha because it's two-tail. Be extra careful, that's 2 zeros after the decimal. And what this tells us is that this is going to be a z distribution versus a t. If we didn't know the population standard deviation is a t distribution. All right, so let's find our critical values. So inverse norm, 0.005. Those are -1. -2.58, we'll say. Making this one a positive 2.58. You inverse norm again and do the 1 minus trick. So there's our critical values. Let's talk test statistic now. Test statistic. Now this is going to be test. And we have our data. So first off, our mu is going to be 150. Our known standard deviation is the 16.4. 16.4. And I have my information in list 1. And just as a reminder, the way that I put list 1 in there is it's above the number 1. So I hit shift or second 1, and that changes it to list 1 for me. Also, this is the frequency is just 1. This is a 2, and we're going to calculate. And they tell us that z is about equal to 0.7538. That, and I'm going to over-exaggerate this, is about right there. And our overall p-value, 0.4510. And the point is that this is way bigger than our alpha. So we are definitely going to fail to reject in this case. So let's come to a conclusion. There is not sufficient evidence to support. Remember, I changed the claim. I made this the claim. So made it not equal to. The mean weight is not, and that's the change that I made, 150 pounds. And that is 37. And number 38 is here. So we're going to test a claim that the mean lifetime of car engines of a particular type is greater than 220,000 miles. Sample data are summarized here. And I want to make note, they did not give us any information at all about the population standard deviation. So this is definitely going to be a t-test. So we have null hypothesis. The mean is larger than 220,000. And the claim, oops, this should be equals. This one's bigger than 220,000. Null hypothesis is always the equals. And the information they give us, they give us alpha is 0.01. They give us X bar is 226, 450. That was when N is 23. And this is not the population standard deviation. This is the sample standard deviation. So it's going to be a t-test. And so let's set up our critical region. And because it's larger than, it's going to be a right tail. .01. So I do inverse norm. And again, area to the left. So it's going to have to be 1 minus 0.01. So my critical value is 2.326. And let's find the test statistic now. This is an 8. Yeah. So our test statistic is going to be, this is again, a t-test. T-test. And I definitely don't have data in this case. I have stats. So the mu in this case is 220,000. Oop, I think I put too many. 1, 2, 3. Yeah. The mean 226. Not 0.450. Standard deviation is 11,500. N is 23. And this one is greater than . Yeah. All right, here we go. bringing that t is about 2.6898, which is about right there. Exaggerate that a little bit. So we are in the zone in this case. P-value. And once again, the point is this is way less than our alpha. Not way less, but significantly less. So what conclusion can we pull from this? We can conclude that we're going to reject the null hypothesis. Meaning there is sufficient evidence to support the claim that the engine-less car's engine, make sure I'm wording this right, car engines, yes. Car engines last longer than 220,000 miles. All right, I'm gonna see if I can squeeze number 39 to the bottom of this. All right, the standard deviation of math test scores at one high school is 16.1. A teacher claims that the standard deviation of the girls' test scores is smaller than 16.1. A random sample of 22 girls results in scores with a standard deviation of 12. Use the significance level of 0.01 to test the teacher's claim. So this is gonna be a chi-squared distribution. Let's start with our null hypothesis. 16.1. And she's claiming the girls are less than 16.1. So this is gonna be a left tail. And they give us that the sample standard deviation is 12, N was 22, and alpha is 0.01. All right, let's set up our chi-squared distribution. And this is less than, so it's a left-tailed. And remember, chi-squared distributions start at 0. And the area there is 0.01. And we need a critical value, so we need a chi-squared table. Now, keeping in mind, n is 22, which means our degrees of freedom is 21. And also keep in mind, our table only knows area to the right. So this is 0.99, right? The whole area on the whole curve has to be exactly equal 1. So if this is 0.01, then 1 minus that is 0.99. So let's bust out the table. So here, area to the right is 0.99. Our degrees of freedom are 21. Over there, yes. So it looks like my critical value is 8.897. And our test statistic uses this formula. This one here, to get our test statistic. Now, n minus 1 is 21. S is here, 12 squared over sigma, 16.1. Let's see what we get. That should be squared. I did 12 squared in my head, which is 144, divided by 16.1 squared. There's my test statistic, 11.666, which is right about there. So you can see we are not in the critical region. So we are going to fail to reject. The null hypothesis. So there is not sufficient evidence to support the claim that the girls' standard deviation is less than 16.1. All right. Moving on to number 40. Number 40. A researcher finds that of 1,000 people who said that they attend religious services at least once a week, 31 stopped to help a person with car trouble. Of 1,200 people interviewed who had not attended a religious service at least once a month, 22 stopped to help a person with car trouble. At the 0.05 significance level, test the claim that the two proportions are equal. Now we have two proportions. And I'm going to again change the problem and say that this is the claim. Again, I want us answering with the same types of sentences each time. All right, so we have, let's say they gave us an alpha of 0.05. And this is going to be two-tailed because of the not equal to. And I'm going to use inverse z for this. So second distribution's inverse norm is going to be 0.025. That would be the left one. So this one would be negative 1.96, and this one will be positive 1.96. You would do inverse norm with the 1 minus 0.025 to get that. All right, now we have our zone here. Let's move on to our test statistic. And you'll be using a 2-prop z-test for this one. So stat tests 2-proportion z-test is right there. And before we get going, they actually give us this information. So this will be the religious people will be first. So x sub 1 is 31. N sub 1 is 1,000. X sub 2 is 22. X sub 2 is 1,200. And what else? So here we go. So x sub 1 is there, 31. N sub 1 is 1,000. X sub 2 is 22. N sub 2 is 1,200. Not equal to. And boom. This tells us that our test statistic is 1.9293, which is 1.92, ooh, barely in the zone. I'll exaggerate just a little bit. And our p-value is 0.05369, which is just barely bigger than our alpha. This one's close. Had we chosen our alpha to be 0.01, we would have easily been able to reject the null, but not quite close enough in this case. So in this case, we're going to fail to reject. So there is not sufficient evidence to support the claim that the proportions are, and I changed it, not the same. So that's my addition to it. All right. Number 41, I'm going to show you on my screen. Now for 41, I want to point out a couple of things. Here we have two populations, and this is means about two populations. A couple of important statements here. Assume that the two samples are independent, simple, random, normally distributed. That's fine. Do not assume that the population's standard deviations are equal. So by not assuming that, that means that we are not pooling when we get to our two sample t-test. So the answer is no on the pooling. Because of this, do not assume that the population standard deviations are equal. So let's flip back. Oh, it did work. All right, 41. So a researcher was interested in comparing the resting pulse rates of people who exercise regularly and those who do not. Excuse me. Independent sample of 16 people, there's our N, who do not exercise regularly, and 12 of those who did. And the summary is below. They want us to test at a 0.025. That's an odd one. Who do not exercise regularly is larger than, so we don't have to split it up. So let's start with our null hypothesis. This is our mean is equal to, oh, I'm sorry. This is a two sample. So the first mean, test the claim that the mean resting pulse rate of people who do not exercise regularly is larger than U sub 2. So these are the people that don't exercise regularly. Number two people are the people that exercise regularly. And it says that in the data there now that I'm looking at it. And our alternative hypothesis, let's start that over. Our alternative hypothesis is there. And they give us lots of information here. Before we do that, let's set up our critical region. All right, because it's greater than, that means it's going to be right-tailed. We're going to choose the smaller of the two ends to come up with our degrees of freedom for this one. So n sub 1 is 16, n sub 2 is 12. So we're going to say our degrees of freedom is 11. And so I'm going to do inverse t. I'd like to make it clear you may not have an inverse t if you have an older TI calculator, if you have like TI 83. So you'll have to look it up on the table. And I'll show you how to do that here in just a second. Let's clear that. So distribution inverse t. This is area to the left, so I'm going to do my 1 minus 0.025. Degrees of freedom is 11. So this is 2.200, or 201, what that's going to be. And those of you with the TI 83 that have to look up on the table. In one tail, we have 0.025. In one tail, 0.025. Degrees of freedom are, there it is. All right, next up is our test statistic. And this is a 2 sample t-test. Two sample t-test right there. And we do not have data, we have to use stats. X sub 1 they give us, that's 73.2, 73.2. S sub 1 is 10.9. Sub 1 is 16. X bar sub 2 is 68.2. 9, pardon me, 68.9. Standard deviation 8.2. And N is 12. Now remember, we are not pooling. This is a greater than scenario. And so when asked us about pooling, the answer is no. Now I know they give us there's different ways of calculating the degrees of freedom. So we erred on the side of caution, which is fine. P-value is 0.1222 actually. And I want to point out that my test statistic, I'm going to over exaggerate this, is right there. And the big point is our p-value is bigger than our alpha. So we are going to fail to reject. The null hypothesis. Make sure I'm not. Here we're good. There is not sufficient evidence to support the claim that the means are the same. I'm going to say the not people not exercise regularly is larger than the other. This is just lazy at this point. right. Number 42. That was my messiest one yet. I apologize. Hopefully you can make your way through that. 42. Here we have dependent samples. So the one sample depends on the other, and I very nicely have already put here, it says test the claim that the tutoring has an effect on math scores at the 0.01. Okay, so let's do our proper setup first before we get to the calculator. H naught is that has an effect. So the after should be larger. So when I subtract, it should be less than. So the way I'm getting that is if they have tutoring, then their score should go up. So when I take the before score and subtract the bigger score, I should get a negative value. So that's why it's less than, which makes this left-tailed. This is a t-distribution. Give us an alpha of 0.01. And I want to find that critical value. Now, I want to notice that there are 1, 2, 3, 4, 5 pairs. This means that n is 5, which means our degrees of freedom is 4. So let's do our inverse t. Second inverse t. And area to the left, it's just 0.01. I don't have to do the 1 minus because it's already on the left. Degrees of freedom is 4. Let's see what we get. Ooh. Negative 3.7469. All right, so that's our critical value. Let's find our test statistic now. So this is going to be, this is what I was going to show you a minute ago. Now, I've already loaded in. You may need to pause the video so that you can load it in. I loaded in the first list into list 2 and the second list into list 3, and I'm going to do a little trick. I'm going to take the differences of each one and I'm going to throw it into list 4. And I want to make sure you can see what I'm doing here. A bit of a glare there. All right. So I'm going to do this. I'm going to go up into where it says L4, and I'm going to go list 2, that's second 2, minus second 3, and it's going to subtract all those for me. Look at that, isn't that nice? Now, list 4 is what I'm going to run the t-test against. So quit out of that. So we're going to go stat. This is a t-test, and I have data in this case. Here we have, this is 0. We are in list 4, that's second 4. So change it to list 4 for me. This one is a less than scenario. And calculate. Here we go. All right, so my t-value, my test statistic is negative 2.1336, we'll say. And we can see that's about there. Again, I'm over exaggerating it. Our p-value, 0.04999. Now, once again, the point is this is way bigger than 0.01. Now, had we made our alpha, if it was 0.05, we'd have a different story, barely. But this is pretty definitive. So for this, we are going to fail to reject. The null hypothesis. So there is not sufficient evidence to support the claim that the tutoring helped. Kind of depressing, especially in a math class. All right, new sheet of paper. Last two problems. So number 43. All right. So 43, we are talking, this is linear regression, excuse me. And it's going to be 6 in this case. And it generates an R of 0.789. And we have two options for the best predictor. One of them is our linear regression line. In this case, or Y bar, the mean, which is in this case is 19. All right, so we will need another table. We need this one here. Correlation coefficient, R. Once again, N is 6. And it doesn't give us an alpha, but I'm going to pick the smaller, or the less aggressive one, the 0.811. I'll show you why I do that here in a second. So with linear regression, we have this. And when we look it up on the table, the 0.811, that is my boundary. And to be clear, we're going to assume that there's no correlation, which is what R equals 0 means, or rho in this case. And we're going to, hopefully there is a linear correlation. We can show that there is a linear correlation. So in the middle here, if any of the R values, these are R values. If it's between here and here, there is no correlation. However, if it's between here and here, there's a correlation. And our R that's given is the 7.789. 0.789, that falls short. So in this case, there's no linear correlation. So the best predictor is the mean. Now, if there was a linear correlation, then I would take the X value that they gave us, which is X equals 5, and I would plug it into my linear regression equation. All right, 44. It is 9 in this case. Again, they don't give us an alpha, and you'll see why. Notice it didn't matter if I was here or if I was over here. It was still on the inside. N equals 9. We have R is 0.867. We have a linear regression line of 19.4 plus 0.93x. Or we would choose X bar if there was no linear correlation, which is 64.7 in this case. And once again, N equals 9. And I'll give it the best shot that I can. 0.7 0.96, and you can see the 0.666 is even further in. So I'm going to go the furthest out I can, 0.798. I already forgot what it was, 0.798, I think, 9.798. So here's my threshold. Once again, between here, there is no correlation. But if I'm here or here, there is a linear correlation. And our R value, goes right there. So we're in the correlation zone, which means, so there is a linear correlation. So y hat equals 19.4 plus 0.93x is the best predictor. Am I still on the screen? Barely. Predictor. And they specifically ask us, let me move this up. So at x equals 48, y hat is going to equal 19.4 plus 0.93 times 48. Let's see what we get. 19.4 plus 0.93 times 48, 64.4. 0.04, pardon me. So this is the best predictor. Good luck on your final exam. I hope you guys nail it.